Routh criteria, we can apply to check whether these things are stable or not. One of the conditions is that all the coefficients A, B, C, D, E should be greater than 0. There are other conditions also will come, but first we'll take this A, B, C, D, E greater than 0. That means when you expand this matrix and put the aerodynamic values, coefficients, etc., then you see what is the value of A, B, C, D, E. One thing you have to ensure that if it's dynamically stable, then all the signs of A, B, C, D, E should be greater than 0. So one of those cases I will take, say, what do we mean, what additional information we get when you say E greater than 0, right? So that is the case now I will be studying. Okay, we will talk about a little bit of Laplace transform, a little bit of Routh criteria in our subsequent Man Ki Baat session, but we have to complete this part, so I'm just for time being you take that Routh criteria, one of the conditions is A, B, C, D, E greater than 0. And we are trying to look for the significance of this sort of a huge expression. What is the meaning of this expression? How best we can take care of it. So we are taking a case where E greater than 0 means what? E greater than 0, let us say theta 1 equal to 0, okay? And we are not considering thrust part, which we are not considering because we know it can be easily done similar way. If theta 1 is 0, then I have got E is equal to m alpha ZU minus Z alpha mu greater than 0. Because you can understand if theta 1 is 0, this is 1, and G is always positive, so E greater than 0 means m alpha ZU minus Z alpha mu greater than 0. Correct? So this is the condition. The question is, what does this tell us? Let's go back. What was m alpha? M alpha was defined as Q1 S C bar Cm alpha by Iyy, and then second term is Zu. What is this Zu expression is minus Q1 S Cl alpha plus Cd1 by m. And what is your Z alpha? Z alpha is minus Q1S Cl alpha plus Cd1 by m. And what is mu? Mu was derived to be Q1 SC bar Cmu plus Cm1 2Cm1 by Iyyu1. Right? So what is the condition? E should be greater than 0, because we know that as per Routh's criteria, you take it for granted at this point that all the coefficient A, B, C, D, E for that equation S4 plus BS3 plus C square plus DS plus E equal to 0, all the coefficients should be greater than 0. So we are taking a case where only E is greater than 0. That is, I am seeing what does E greater than 0 mean to us. Okay. So now from there we are studying a case where we are saying let theta 1 be 0. What is theta 1? Theta 1 is the theta at the time of cruise. Okay. Now again we know what is the expression m alpha Zu, Z alpha and mu, which we have already derived. Now we will put this here and see what does this finally mean to us. Okay. So there is a lot of involved, it's involved a lot of board work, so don't get upset. If E greater than 0 means you see that m alpha Zu minus Z alpha mu greater than 0. That means m alpha by Z alpha should be greater than mu by Zu. No issues? We are seeing that we are trying to understand what additional information pertaining to stability we are getting through these coefficients. We know for dynamic stability, all this A, B, C, D, E should be greater than 0. So we are studying a case for E greater than 0. E greater than 0 means this expression greater than 0, which tells me m alpha by Z alpha greater than mu by Zu. And now I substitute the m alpha, Z alpha, mu, Zu in this expression, and then what will happen, you see, m alpha by z alpha will be nothing but, let me write q1 sc cm alpha by iy, that is y, that is m alpha q1 sc cm alpha iyy divided by z alpha. Z alpha is minus q1s cl alpha plus cd1 by m, right? q1s cl alpha cd1 by m. So if I divide this, I get expression minus m c bar cm alpha by iyy cl alpha plus cd1. Okay? So what is the final relation? M alpha by Z alpha is this. Okay. Similarly, we find out what is the second term, mu by Zu. Second term is mu by Zu. So mu by Zu, when I am doing, I know the expression of mu, so I put q1 sc bar by iyy u1 into cmu plus 2 cm1, this divided by minus q1s clu plus 2 cl1 by m u1. You can see that you have to substitute the expression for Zu, and if you see Zu here, oh, this is wrongly written. This is the so let me correct it, and you all should correct it. This should be Zu should be minus q1s clu plus 2cl1 divided by mu1. Okay, so that was wrongly written. Please correct it. So here it will be q1s clu plus 2cl1 by mu1. So once I do that, I get an expression is mu by Zu is equal to minus m c bar cmu plus 2 cm1 divided by iy clu plus 2 cl1. Please understand, you should do it yourself, otherwise there is every possible chance of getting mixed up, you know. Writing this expression is not a simple thing, it is real challenge. You have to should not get defocused. Okay, so what is our aim? We are trying to extract maximum information from this relationship, which has come because of the condition throughout criteria that all the coefficients of that equation A, B, C, D, E should be greater than 0. So we are exploring what happens, what information you get from the condition E equal E greater than 0. So from there we have come here, and now we know these two expressions. One is m alpha by Z alpha, we know this, and mu by Zu is this. So now we will write like this, that minus m c bar cm alpha by iyy cl alpha plus cd1. What is this? This is basically your m alpha by Z alpha. See, m c bar cm alpha iyy. This should be greater than mu by Zu is this expression, and that is minus m c bar cmu plus 2 cm1 divided by clu plus 2 cl1 to iyy. Right? Clu plus 2 cl1 iyy mc cmu. Now how to simplify this? We know the cm1 is 0. This is the at trim. This value is 0. At trim, our trim is cruise. This value is 0. So now further, if I manipulate this expression, we get very interesting result. And all these efforts were for that. If I further simplify this, I'll get minus cm alpha by cl alpha plus cd1 is greater than cmu by minus cmu by CLU plus 2CL1. You could see here, this MM gets cancelled, CC gets cancelled, IYY gets cancelled, CM1 is 0. So this is nothing but MU, CMU. Okay, so that is what is prevailing here. CM1 is, of course, is 0. Now, if I say CD1 is less compared to CL alpha, it's very true. CD1 could be 0.025, CL alpha will be around 5.5. So this is a good approximation. And then what we get? We get this is as CM alpha by CL alpha less than CMU by CLU plus 2 CL1. You could see the sign has changed to less than, because there is a minus minus sign. When I multiply minus on both sides, naturally this becomes this. What is the meaning of CM alpha by CL alpha? Let us understand. What is this ratio CM alpha by CL alpha? This is nothing but DCM by DCL, right? And what is this? This is, minus static margin. So what you are getting from here, that DCM by DCL should be less than CMU by CLU plus 2CL1. For dynamic stability, the condition is that DCM by DCL should be less than CMU by CL1 plus 2CL1. Now, for a subsonic case, CMU is equal to 0. So naturally, we have this condition, DCM by DCL less than 0. We are okay with this, right? But for supersonic case, CMU will be negative, right? CMU is negative. Supersonic case, CMU is less than 0, that because CMU is nothing but M1 into DCM by DM. And what happens? As the aircraft goes supersonic, increase the speed, the center pressure or the aerodynamic center of the tail goes backward. So this tail momentum increases, so that gives you a nose down moment and the tuck under effect, right? So this is negative. So DCM by DCL is again negative. What is the difference? In the first case, when CMU was 0, DCM by DCL should be negative, it is okay, statically stable. Second case, also DCM by DCL should be less than 0, because this is negative. So again, DCM by DCL should be less than 0. So there is no violation on the static stability. However, what is the difference? Let us see that. So we see here that DCM by DCL is equal to, or should be less than, CMU by CLU plus 2 CL1. We know CMU is negative for supersonic case, so DCM by DCL less than 0 is fine. But what is, let's say this number for supersonic case, is A star. I can get the value of CMU, I can get the value of CLU and CL1. So this is negative, that we know. So this will be indeed less than 0. So DCM by DCL, okay, let this equal to A star, where A star is less than 0. Fine? This is supersonic case. For subsonic case, same relation is giving DCM by DCL is less than A star, less than 0, because CMU is 0. Because CMU is equal to 0, here CMU not equal to 0, in fact less than 0. What is DCM by DCL? DCM by DCL is, that you understand. Let me erase this part. So what is DCM by DCL? We have seen DCM by DCL, right, is nothing but minus static margin, that is minus x or minus neutral point minus xcg bar, or we can write as xcg bar minus n0 bar. N0 is the neutral point. For subsonic case, what it's just simply telling that if this is the N0, Okay? The aircraft will be, for subsonic I am writing, right? From there, what I am saying, getting is dCm by dCl should be 0. That means xCg could be anywhere, as long as it is in this side. Correct? But for supersonic case, what is dCm by dCl when it takes care of dynamic stability also? It said it is not just not less than 0. It is also to be ensured that dCm by dCl is less than A star, where A star is negative, which is given by CMU by CLU and 2CL1. So that means just putting CG here ahead of N0 will not be sufficient. You have to ensure that the CG is such that xCg minus N0, this separation now will be governed by, it should be less than A star. That is, this distance, okay, if I say B, for supersonic case, this B should be less than A star. Okay? Is this part clear? dCm by dCl should be less than A star. Please note that A star is negative. This is positive, and this you can even neglect, very small. This is positive, this is negative, so this value is less than 0. This is fine. So that is what you should be very, very clear, that for dynamic stability, the supersonic case, how CMU, which is nothing but M1 dCm by dm plays an important role through a phenomena called tuck under, which is as speed increases supersonic, AC of the tail goes backwards, so tail momentum increases, so additional nose down moment comes, which is known as tuck under effect. Okay? So this is clear. So in a nutshell, the CMU plays an important role which restricts the stability margin to ensure it's also dynamically stable. And this we have derived from the condition that E is greater than 0, okay, which is a condition for dynamic stability through Routh criteria. Okay? So we try to revisit this E greater than 0, this condition which came from the characteristic equation AS4 plus BS cube plus CS square plus DS plus E equal to 0. And you know from Routh criteria, one of the conditions to satisfy is all these coefficients should be greater than 0. And there are other conditions which will come, right? And by using this condition, one case, E greater than 0, what does this mean? And we got a relationship, wonderful relationship. We got dCm by dCl less than CMU by CLU plus 2CL1. Okay? And you know, from this relationship, we realize that if CMU is equal to 0, this implies simply dCm by dCl less than 0, which is, we are very familiar, the slope of Cm versus Cl at equilibrium should be less than 0. But at high speed, if CMU is not equal to 0, then what? Then, let's say at high speed, CMU, we know, is nothing but M1 dCm by dm, and which is less than 0. Then this condition says dCm by dCl should be less than A star. But what is A star? A star is nothing but CMU by CLU plus 2CL1. Typically, let's say this value, okay, is equal, let's say, minus 0.1. CMU is negative, okay? If this is minus 0.1, for say, this is an example we are telling to understand this, say this, that means then the condition is just not dCm by dCl less than 0. The condition is dCm by dCl, yes, indeed less than 0, but should be less than 0.1. That is the modified condition when you are taking dynamic stability also into account. So the location of neutral point and the CG becomes extremely important. Yes, it has to satisfy this condition as well, which includes the condition that dCm by dCl is less than 0. But it is dCm by dCl less than this value of this, which say, for example, we have taken minus 0.1. This should be understood very carefully. Okay? Why this is important? Because we are taking care of the fact that I know as speed increases, the AC of the tail goes backward, and there is a tuck under phenomenon. Okay? So this is one. And then another way to be friendly with this big equation is to see that what finally these expressions are meant for us. Let's take an example. Let's say for a business jet airplane, all those derivatives were computed, and after solving, we found that the value of A, B, C, D, E, which are dependent upon the geometric and aerodynamic coefficients or derivatives. Let's see the A value of A is 675.9, B is 1371, and C is 5459, and D is 86.3, and E is 44.78. And let's say these are all in FPS unit. At this point, let's talk about the signs and all. You could see A, B, C, D, all are greater than 0. So one of the condition or all criteria for stability is satisfied. Okay. Now, if I now solve this equation and try to find out the roots through numerical methods, which is possible, and let's say that it has been done, and the roots are lambda 1, 2, roots are minus 1.008 plus jth complex 2.651, and another pair of roots 3, 4, which is minus 0.0069 plus minus j small j 0.0905. Typically, you'll find most business jet airplane, if you get those aerodynamic coefficients and solve this equation, you'll find it will get segregated into this. One pair here, one pair here. So, two second order system behavior. That's the beauty of longitudinal dynamics. You'll find for most of the airplane, its response will have two types of excitation. One thing is that they are having complex pair, means they're oscillatory in response. Okay? For a stable system, oscillatory response. That's why the roots are complex here or here. But what is the difference, you see? The first pair, you find this real root. First pair. Okay? This typically you will see for most of the airplane. First pair, this is real, negative. Right? And it's very large compared to the second pair. Large compared to second pair. You could see here is minus 1.008, here is minus 0.0069. What does this real root does, or real value of this root does? You know that this real, if its real part is negative, that means it will typically form of e to the power minus t nt, right? It will put an envelope of decaying. You know? The temperature will go on decay. If the real root is positive, then it will go on growing it. The root will go on growing, because this is typically e to the power lambda t. If lambda 1 is negative, the real part is negative, which is here. Both are negative, that means both are trying to cut down the amplitude, and it is oscillatory also. So, if you see, the root will typically look like, so this envelope will be governed by the real negative root, and wherever this root is large negative, they will decay fast compared to the slower one here. So, I could see that there are two modes that are excited where one is decaying very fast, another is taking long time. So you get long period. This is long period. And this is short period mode. Short period mode. And both are behaving like a second order system, both this mode. Right. Now, come back to the airplane. What happens if the airplane is moving like this if you give a disturbance? Then one way it gets excited is does like this and comes back to the equilibrium. Another could be it goes on doing like this and then finally comes back. The second one, this one, is nothing but the longer period. Its real root is small negative. First one, which one is this short period, is this one. So we will characterize this lambda 1, lambda 2 as short period root, and these are long period root, or we also say phugoid roots. Right. We'll discuss about short period and phugoid mode in detail, but just see if this beautiful equation, although looks ugly in terms of expression, but how informative it is. Now, how do I handle what information more I should be able to extract from this? If it is a second order system, what I look for is natural frequency. I look for its damping ratio. So let us see, can I use this equation to find short period natural frequency or long period natural frequency and damping ratio. Let us do that. If I take this, since I have seen this is a typical second order response, so I write this as characteristic equation as s square 2 zeta omega ns plus omega n square equal to 0. This is typically second order characteristic equation in terms of omega n and zeta. And so I construct equation from this root in this form. So I'll write s square minus sum of the roots into s plus product of the roots equal to 0. So if I take this first equation or first root for lambda 1, 2, this equation becomes s square minus sum of the roots will be what? Minus 1.008 plus j into 2.6. This is plus minus. Okay. J 2.651. Right. So this is one root plus again minus or plus minus 1.008 plus this is minus now j 2.651. Okay. This becomes the sum of the roots. The first root is, I missed that minus sign here, plus minus the complex pair. So one root is minus 1.008 plus j 2.651. Second root is minus 1.008 minus 2.651. This is sum of the roots into s plus product of the root. How to find product of the root. So this would be minus 1.008 plus j 2.651 into minus 1.008 minus j 2.651, and that equal to 0. If you do like this, you will get equation in this form, s square minus sum of the root into s plus product of the root, and compare it with this equation, and you will get s square minus this and this get added. So this becomes plus, that is 2 into 1.008, then I've got plus product of the root, so that will be minus 1.008 plus 2.651j, okay, into minus 1.008 minus 2.651j should be equal to 0. This is nothing but a plus b into a minus b. So you will get equation where 2 into this into s will be there. It will be s here. Let me erase this. To s plus. So I know I have to compare this with this equation. So s square and then plus 2 zeta omega n s. So for 2 zeta omega n, I will write this equal to this, compare with this, and omega n square I'll compare with this product. Should be typically will be minus 1 point a plus b into a minus b. So a square minus b square, and j is there, so that become a square plus b square. That will be typically, if I am not mistaken, this value will be minus 1.008 whole square plus 2.651 square. So the a plus b into a plus jb into a minus jb will be equal to a square minus jb whole square, which will be equal to a square plus b square. So you can see that this product will be a square, that is minus 1.028 square plus b square is 2.651 b square. This would be equal to 0. So I'll compare omega n square equal to this term and 2 zeta omega n ns equal to this term. And by solving that, I'll get omega n equal to 2.836 radian per second, and zeta I'll get around 0.355. Is this clear how to do it? So you could see I could use this equation and find out the roots. Similarly, for this also I can find out a similar way, and you are supposed to do it and find that omega n 34 will be equal to 0.091 radian per second, and zeta equal to 0.076. And you could see that the zeta for first one is very, very high compared to the second one. That is why second is this, we call it a phugoid mode, long period mode. It goes on doing like this, go on converting kinetic potential energy among each other, and then there's losses, and it comes back to equilibrium. And the first one is simply like this. So that's why the zeta is 0.355 compared to 0.076. Same thing is reflected in omega, you see. This is much larger short period than omega n phugoid. Okay. So this you must do one exercise yourself. This is a very straightforward thing. We'll solve one or two examples of this so that you are handy. This lecture was meant to give an idea how to handle this big equation and get some relevant number. Here today I will end. In the next class I will start from here. I'll solve another example so that you get familiar to what we are doing.